The birth of a black hole. How does it form? The universe is a strange and intriguing world full of secrets and extraordinary happenings. This is most likely why some individuals are terrified while discussing space and astronauts. And what could be more terrifying and appealing than a black hole? Hundreds of papers have been written about these extraordinary objects, which are also the most intriguing topic to study in astronomy. When the Event Horizon Telescope captured the first photograph of a black hole last year, revealing the spectacular hole located in the center of the M87 galaxy, the whole scientific community and even the entire world population was completely enthralled. Consider them to be extremely massive amounts of mass accumulated in small volumes with such a strong gravitational attraction that nothing, not even light, can escape from the object. In fact, their name provides a fair symbolic explanation. Like holes, everything continues to sink into them with no way out. Abandon all hope, you who enter here, reads the inscription at the gates of hell in Dante's Inferno. This would be an accurate description of the phenomenon, but don't worry, you won't be eaten by a black hole. Instead, have you ever considered the origins of these objects? How do they form, and how long does it take for a black hole to birth? How can we learn more about the origins of this phenomenon? These and other questions will be addressed in this video, so stick with me and I'll tell you everything in a moment. Hello and welcome to Zeey. Subscribe the channel and follow us. We're going to look at one of the most important items in modern physics, therefore we'll go through the process step by step. Who was the first to propose the existence of black holes? In a letter published in November 1784, astronomy pioneer and English clergyman John Michell introduced the concept of a behemoth so huge that even light could not escape. When physicists discovered the wavy character of light in the 19th century, however, Michell's theory was abandoned because it wasn't obvious how and if gravity could interact with light radiation. To summarize, let us go straight to 1915, when maybe the most exciting idea in physics was published by a Swiss man. Do you know what it's called? Albert Einstein. He first proposed special relativity in 1904, its renowned Annus Mirabilis, in which he also published an article on the photoelectric effect, which earned him a Nobel Prize in 1921. Around 10 years later, in 1915, he published General Relativity, its most important work and one of the most fundamental theories in physics. But what does General Relativity say? How can we grasp such a complex model intuitively? Shortly after, Einstein attempted to apply his special relativity to gravitational events such as planets orbiting a star or stars colliding at high speeds. He discovered a crucial result: the mass of an object deforms space and time. What does it imply? Consider the space-time continuum to be a large cloth sheet. When a mass sphere, the Sun, is placed in the center, the sheet curls. If another lighter object tries to travel in a straight path through the sheet, it begins to circle the first one due to the curvature of the sheet. How does the mass of a star deform time? When you're close to an object, time dilates and slows down. Furthermore, the slower the flow of time, the heavier the body. What is the significant outcome of this model? Because light must follow the curve of spacetime, it is impacted by gravity. For example, if a large black hole is positioned between us and a bright star, light will deviate due to the deformation caused by the hole's mass. However, Einstein was not the only one who made significant contributions to discovering the theoretical existence of these particles. In fact, barely a few months after its publication in 1915, scientist Karl Schwarzschild discovered the solution to general relativity equations for a spherical mass and a point mass. Just a few years after Schwarzschild, Johannes Droste, a Hendrik Lorentz student, independently gave the identical solution for the point mass and wrote extensively about its features. This solution behaved strangely at what is now known as the Schwarzschild radius, where it became singular, implying that some of the terms in the Einstein equations were infinite. What were the two most peculiar features of these singularities? For starters, the gravitational force would be so strong that light would be unable to escape, with rays falling back to the star like a stone to the ground. Second, the mass would cause such a curvature of the spacetime metric that space would close in on the star, leaving us outside. As a result, the most important discoveries were made during the so-called Golden Age, which began around the 1960s, when black holes were the most prevalent and mainstream field of research. The surface circumscribed by the Schwarzschild radius was given the renowned label Event Horizon by David Finkelstein in 1958. What exactly does this definition imply? The event horizon is roughly defined as the border inside which the black hole's escape velocity exceeds the speed of light. To be more specific, it is the point at which all conceivable light paths begin to sink into the black hole, with no way out. Does it appear difficult? Don't worry, here's an easy analogy. Within the event horizon, all light is guided into the hole in the same way that we go forward in time. It is an immutable order of the phenomenon that cannot be changed. And do you want to hear anything frightening about these weird objects? When an object falls into a black hole, any information about the object's shape or charge distribution is evenly spread throughout the black hole's horizon and is lost to outside observers. What does it imply? In practice, we can think of the object as a dissipative system like a membrane with friction or electrical resistance. Whatever vanishes in the hole is completely unavailable to outside observers. The black hole information loss paradox refers to this peculiar behavior. But let's get back to the major point of this video. What causes a black hole to form? To address this question, we must first discuss stars. Stars? Why? Because practically everything in astronomy is tied to these breathtakingly beautiful gleaming celestial bodies that illuminate our dark night sky. Scientists have discovered that stars evolve differently depending on their mass. They are primarily distinguished by the nuclear reactions that occur in their core. Nuclear fusion is critical for the creation of life because the reactions generate enough radiation to warm the planets orbiting around them and even balance the gravitational attraction that would cause the celestial body to collapse on itself. How is that even possible? According to Einstein's famous equation E=mc², nuclear reactions dissipate a relatively small portion of the mass involved in the process, generating enormous energy. These massive amounts of energy are subsequently radiated as electromagnetic radiation at various scales: visible light, UV rays, gamma rays, or microwaves. These emissions have the ability to not only heat materials, but also exert a tenuous pressure on particles. In fact, the radiation released by stars functions like a wind, balancing gravitational contraction. Although radiation pressure is meaningless on Earth, it may be seen clearly in space. As a result, Japanese researchers were the first to launch the Icaro probe, which uses stellar wind to travel in space, in 2010. In terms of star evolution, heavier stars have shorter lives because they use hydrogen and other key elements, such as helium, for nuclear processes at a higher pace. Throughout its existence, the star spends varying amounts of time in various stages, depending on the major element that is burning in the core. The process of nuclear reactions in the core of gigantic objects 8 or more times heavier than our Sun comes to a halt with the formation of iron. But why? Because fusing of its nucleus would need far too much energy. What is the end outcome of this? The internal pressure of the star, which was previously provided by radiation pressure, drops drastically and fails to oppose gravitational contraction, resulting in what we call a gravitational collapse. In practice, the star collapses under its own weight because there is no longer any pressure to balance the natural contraction. Now comes the important question: is there an inferior limit for the collapse of the star? Yes, indeed. It is also related to the exceptional theory of quantum mechanics. The Heisenberg uncertainty principle, which asserts that we cannot know both a particle's position and momentum, is the most essential principle of this paradigm. More exactly, it specifies that the product of an object's uncertainty in location and angular momentum must be greater than a constant amount. So if we know a particle's coordinates very well, we will have a large mistake in its momentum and vice versa. Along with this, it is necessary to explain another idea known as the Pauli exclusion principle. In a nutshell, it argues that two separate fermions, a type of particle that includes the electron, cannot be in the same quantum state. What does it imply? That is, if two particles are in the same position, they must have different momentum. What are the implications of applying these ideas to a collapsing star? In rare situations, the contraction is stopped by what is known as degeneration pressure. The more densely particles are packed together and forced to share the same space, the more they must differ in terms of momentum, and the greater the range in momentum, the greater the fraction of particles with high momentum, and these exert pressure on their surroundings. As a result, this process allows matter to condense into an unusual denser state. As a result, one of the several forms of compact stars is formed. The mass of the remnant of the parent star left after the outer layers have been blasted away determines which type forms. The mass of the remnant, the collapsed atom that survives the explosion, may be significantly smaller than the mass of the original star. Stars with masses greater than 20 solar masses produce remnants with masses greater than 5 solar masses. The collapse of smaller remnants results in the production of a neutron star, which is a very small entity made of ultradense degenerated neutrons exerting a high pressure that balances its gravitational contraction. If the remnant's mass surpasses roughly 3 to 4 solar masses, either because the original star was very heavy or because the remnant accumulated more mass through matter accretion, even neutron degeneracy pressure is insufficient to stop the collapse. There is no known mechanism that can stop the implosion, and the object will finally collapse under its own weight. This is the birth of a black hole. Do you want to know something unusual about this event? An external observer will never see the end of this process because of time dilation, which is quite significant in these huge expanses of space. What does it imply? A viewer watching the collapse would witness the falling material slow and come to a stop just beyond the event horizon. As time is heavily warped by the large amount of mass, light from the falling material takes longer and longer to reach the viewer. As a result, the external viewer never sees the event horizon emerge. Instead, the falling material appears to become darker and more red-shifted until fading away. Finally, black holes are typically generated by the leftovers of a collapsing huge star that is more than 8 times the mass of our Sun. As a result, several issues remain to be resolved, most notably the possible death of a black body. Many aspects will be investigated in order to provide us with a proper perspective on these magnificent objects that perpetually swallow everything within the event horizon. This video has come to an end. Thank you for tuning in. Did you find this subject interesting? Do you believe that humans will be able to go closer to one of these objects? Tell us in the comments and don't forget to like, share, and subscribe.